All right, in the last video, we talked about creating a titration curve for a strong acid being titrated with a strong base. In this video, we're going to talk about an almost equivalent type of reaction. We're going to use the same concentration of acid and base, just like we did last time. We're going to start with 20 mils, but this time we're using acetic acid, which is a weak acid, rather than HCl, which is a strong acid. I'm actually not going to go through all the legwork of all the calculations because it's a lot of ice method problems and buffer stuff, and it gets really convoluted. And honestly, as long as you get the basic concepts, I'm happy. So we're going to talk through the titration curve itself, just the graph part, and it's going to be similar format. Okay, so this is 0, 7, 14. I don't know if I drew that perfectly to scale, but whatever. And this is milliliters of NaOH, and this is 0, 10, 20, 30. Okay, just like last time. Well, here's the thing. When you start out with a calculation with this, what we did last time was we started out by taking the negative log of the concentration of acid because it was a strong acid, and that's all you had to do. This is a weak acid, so you have to actually go through all the ice method stuff. But what we will find is that the starting value is a little bit higher. Okay? And what happens here, turn over what color I just did the other one in. I guess we'll do it in red. What happens here is that this actually, when you start adding base, this actually goes up for a little while, and then it almost immediately starts leveling out. Okay? And then it curves up and then flattens out. Okay, so at first glance, it's not drastically different than the last one, but I'm going to point out a few things here. Okay? It turns out that this flat area is caused because this is a buffer. And this buffer region is going to occur at a pH plus and minus 1 of whatever the pKa of your weak acid is. Okay, so this has a pKa equal to 4.74. So the middle of this is your equivalence point. Trying to figure out what color to label things in. This is technically your equivalence point. Because we said with a buffer that, so what's happening is as you add NaOH, this is an equilibrium, this shifts to the right and creates CH3COO minus, which is the conjugate base. So what's happening is as you're titrating this, you're actually creating the conjugate base, which is why it forms a buffer. So the equivalence point is when the concentration of acetic acid becomes equal to the concentration of COO minus. So it's not the base that you're adding, but it is a base, and the concentration of acid and base are the same. And we said with the Henderson-Hasselbalch equation that if these two things are equal, your pH equals your pKa. So the pKa right here is 4.74, okay? And it turns out that anything from about 3.74 up to 5.74 is going to be in that buffer region, okay? And so in this graph, the equivalence point and the neutral point are very different things, okay? They're very different volumes. And honestly, it actually takes more base to neutralize this than it did for the strong acid because it forms a buffer region. And the buffer actually resists pH change, so you have to get through this buffer region before it starts spiking up. So this is technically the neutral point, which is a pH equal to 7. Okay. So anytime you have a weak acid or a weak base, what's happening is it's going to, look just like the other curve. Honestly, it's going to slowly go up, but wherever the pKa is, plus or minus 1 pH unit, you're going to get this buffer region where it kind of levels out. If you had something like H3PO4 with 3 protons, you would actually see 3 separate buffer regions before it got up to this flat part of this plateau at the top. Okay, and this is actually one of the easier ways if you can make this graph, if you can just plot pH versus volume of base, where it flattens out is actually the easiest way, the middle of the flattened out region is the easiest way to figure out the pKa's of all the different acids involved. So you can use pKa to get Ka. Okay. So if nobody had, if we hadn't told you that the Ka is 1.8 times 10 to the negative fifth, which we've used in like 15 different examples and in the lab, this is actually one of the ways you could figure it out. You could keep track of the pH as a function of concentration, and literally where this flattens out in the middle is where the middle of that flat region is the pKa, and you could just do 10 to the negative 4.74 to get Ka. Okay, so again, I'm not going to make a huge deal out of this, but I do want you to understand the basic concepts as to why this doesn't quite look like the other one. Okay, if you had something that for some reason had a buffer region more in the basic region, you might actually get to the neutral point before you get to the equivalence point. Okay, so this gets a little muddier. Technically, all the calculations in terms of how you would approach this, here you would do an ice method problem. Here you would actually treat it as a buffer region. You would actually do the buffer thing, and you would just keep track of how much of this has been neutralized and how much of this forms, because however much of this is neutralized is how much has formed, and you just plug it in the Henderson-Hasselbalch equation. And then once you get to this point, it's all been neutralized, and you just keep track of how much base is left over. So, not too bad, not drastically different than what we had seen before, but it does have a little nuance to it. Okay, this is the last video, and so I'm going to squeeze one more little tiny topic on the bottom. So at the beginning of this, at the beginning of chapter 16, we talked about how we need to switch from the Arrhenius definition of acids and bases, which is anything with an H plus is an acid, and anything with an OH minus is a base. There's nothing wrong with that definition, it's just not broad enough. So we switched to the Bronsted-Lowry definition, which is anything that gives up an H plus as an acid, anything that receives an H plus as a base. Well, Lewis, the same guy from Lewis Structures, has his own definition of acids and bases. He actually treated it more like electricity, which we haven't really talked about electricity yet, but we will in a couple chapters. His definition is a Lewis acid is anything that can receive an electron pair. So when we talked about acids and bases, we said that an acid is anything that gives up an H+, and the base tended to have a lone pair on it because it could receive the H+. This is a broader definition where a Lewis acid is anything that receives a lone pair of electrons, either forming a bond or whatever. A Lewis base is anything that is an electron pair donor. This actually feels like the Bronsted-Lowry definition of a base. Electron pair donor. So here's a weird example, just to mess you up before I give up on this topic. Okay, let's look at this reaction. Turns out that BF3 is a molecule, obviously. There's lone pairs. We haven't drawn this one in quite a while, but it's a Lewis structure, Talking about Lewis, might as well do a Lewis structure. It's possible that if there is another fluoride floating around, this would have a negative charge. I'm going to circle it just to keep it separate from the structures. It turns out that boron is fairly positive, and it will attract these electrons. This thing is going to basically donate some electrons and form a bond. Okay? And the boron would have a negative charge, whatever. Okay. Well, by this new definition, this thing is accepting a lone pair of a pair of electrons, so this is a Lewis acid, despite not having a hydrogen on it at all. This thing is giving up a lone pair, so this is a Lewis base. The Lewis base part doesn't seem as weird because we've actually seen F- as the conjugate base of HF. This one isn't weird. This is super weird as far as I'm concerned. And the idea of conjugate acids and conjugate bases gets a little more complicated because technically this is both of those. And because there's an exchange of electrons, you can almost keep track of this in terms of electricity, which actually works out really nicely because you guys may have seen in the lab that when we use acid base or the pH probes, if you're calibrating it, one of the first things it says is, okay, you know, in the lab we set it to a pH of 4. What you did was you put it in the solution and then it measured the voltage of the solution. Because there's electrons being transferred, you can actually measure pH in terms of voltage. They're not unrelated. So this is useful, but honestly, I try to avoid this like the plague. If you can keep track of the Bronsted-Lowry definition, I'm happy, but technically this isn't wrong. It's just a little weird. All right, this is gonna end all of the acid-base stuff. This is everything up to exam 2. All right, thank you.